All right, so the time is 4:05. I think we can get started while the rest are still on their way. So let me show you today's agenda. Before that, actually, I want to mention that there are some guests with us today. All right, we have Mr. Tan and Mr. Chan from SEAB and Mr. Wong from MOE. All right, we have three guests with us today. They are here to observe the lecture, and this is a requirement for university offered history course. All right. Now, the agenda for today is as shown. There are two main topics that we are going to cover. The first one is on the electrical breakdown of the PN junction. And the second topic is on junction and storage capacitances of a PN junction. I understand that the concept of capacitance is not covered in your H2 physics course. So before we actually go into the discussion on the PN junction capacitances, I would go through a short discussion on the concept of capacitance. Okay. So let me get started with the first topic. All right. So the first topic we're going to go through is reverse breakdown of the PN junction diode. Now, at this point, you should be quite familiar with the IV behavior of a PN junction diode. So what you see on the right is a diagram, or is a graph that plots on the vertical axis the current density flowing through the diode against the horizontal axis, the voltage applied across the diode. So when the voltage applied is positive, or in other words, when the diode is forward biased, the current would increase very quickly, right, beyond a certain turn-on voltage, which is approximately the built-in voltage of the diode. On the other hand, if you apply a reverse bias, or in other words, VA is negative, the current is very small. Right, so we have discussed all this last week. Now, what we are interested in today is to understand why, when you keep increasing the reverse bias, there will be a point whereby the current through the diode will also increase very significantly, as shown here. Now, the voltage at which this happens is called the breakdown voltage of the diode. In other words, the PN junction diode has suffered electrical breakdown. Now, there are two mechanisms responsible for the electrical breakdown of a diode. The first one is due to the Zener tunneling effect, and the second one is the avalanche effect. So we'll discuss each of them in turn. Now, before I go into the discussion on the physics, I just want to tell you that reverse breakdown is not necessarily a bad thing. In case some of you think that it is bad because of the way the term is being phrased, reverse breakdown, right? So I just want to tell you something about the practical application of reverse breakdown. In fact, some diodes, in other words, there is this diode called the Zener diode, right? It is actually specially designed to work under reverse breakdown. And one very important application where the Zener diode is operated in reverse breakdown is found in this thing called the voltage regulator. Now, the circuit diagram is shown here. Now, the purpose of the voltage regulator is to ensure that the voltage applied across a load is as constant as possible by smoothing out the fluctuation in the incoming voltages. So essentially on the left, you see the unregulated input. So the voltage here can fluctuate with time, right? And if we connect the Zener diode in this manner, right, we can ensure that the voltage that appears across the load will be kept to a very constant value. The reason is because when the diode is operated under breakdown, it allows a large current to flow for an insignificant change in the voltage. In other words, when the diode is operated under breakdown, the current can flow, a large current can flow through the diode for a practically constant voltage across the diode. Right, so due to this behavior, the voltage across the load, which is also the breakdown voltage across the diode, can be kept to a constant value. Now, the voltage regulator is actually used in the later stage of the rectifier circuit. If you remember this, I showed you this much earlier in the first lecture on PN junction. So one application of the PN junction is in the bridge rectifier circuit like this, which essentially converts the AC signal into a DC signal. Now, even after conversion, there will be some fluctuation in the voltage. And as you can see, there will be a small ripple, right, riding on the DC voltage after the conversion. And the voltage regulator, which involves a Zener diode operator under breakdown, can be connected at this part of the circuit to smooth out the fluctuation in the DC voltage. All right, so I just want to give you an idea that reverse breakdown is not necessarily a bad thing. In fact, it has a very important practical application. Now, having said that, not all breakdown is good. In particular, avalanche breakdown is bad. All right, so we will try to understand why that's the case. Okay, so let me explain what causes a diode to break down. In particular, first focusing on Zener breakdown. Now, Zener breakdown occurs typically in a highly doped PN junction. I will explain why we need highly doped PN junction later, via quantum mechanical tunneling. Quantum mechanical tunneling is a phenomenon whereby an electron wave function can penetrate a potential barrier, and the electron wave function can therefore exist on the other side of the potential barrier. Now, to illustrate this concept on quantum mechanical tunneling, you can refer to this diagram on the right. The vertical axis is the potential energy axis. The horizontal axis is the distance axis. So imagine there is an electron that is moving from left to right like this. Now, along the way, it encounters a potential barrier. Now, why I call this a potential barrier? Because the potential energy here, right, is actually higher than the potential energy of the electron, right? So this presents a barrier to the moving electron. Now, in terms of classical mechanics, there is no way for this electron to surmount this barrier. In order for this electron to surmount this barrier, in terms of classical mechanics, it needs to have a potential energy that is higher than the energy barrier itself, right? But in quantum mechanics, Schrödinger equation says that there is a finite probability for the electron wave function to penetrate the potential barrier and then exist on the other side of the barrier. In other words, if we solve this problem, right, or rather we solve Schrödinger equation for this problem, if we are able to get a real solution for the electron wave function on the right side of the barrier, then it indicates that the electron has a finite probability of surmounting the barrier and getting to the other side of the barrier. Okay, so this concept is called quantum mechanical tunneling, as though the electron is tunneling through the potential barrier. Now, there are three important conditions that must be fulfilled in order for quantum mechanical tunneling to happen. The first one is that the barrier must be sufficiently thin. The reason is because if we have a very thick barrier, then the probability will be very small. In other words, the electron wave function is almost negligible on the other side of the barrier. And the probability will increase exponentially when the barrier thickness is reduced. I won't go through the mathematical derivation for this as it is quite involved. It basically involves the solving of the Schrödinger equation, and we can see that the probability actually depends exponentially on the thickness of the barrier. Now, the second condition is that the tunneling can be enhanced if there is an electric field in the right direction that exceeds the movement of the electron across the barrier. Now, if, for example, if you look at this diagram, if there is an electric field pointing from right to left, right, the electric field will tend to attract the electron to the right side of the barrier. Right, so if there is an electric field that actually is in the right direction, it will favor the tunneling, increasing the probability. The third condition is that there must be a presence of an empty energy state at the other side of the barrier. Basically, I have mentioned this actually. This statement actually is equivalent to the Schrödinger equation having a real solution on the other side of the barrier. In other words, the electron must be able to exist on the other side of the barrier. And in order for that to happen, one can say that there must be an energy state available. In other words, there must be a real solution available for the electron wave function to exist on the other side of the barrier. Okay, so these three conditions must be fulfilled before quantum mechanical tunneling can happen, right? So with this understanding, then the next thing we will try to understand is that whether in a reverse bias PN junction, the three conditions can exist. So if you look at the Venn diagram of a reverse bias PN junction, right? So let's focus on the right diagram. So under reverse bias, we apply a negative voltage to the P side with respect to the N side. So as a result of the negative applied voltage, the energy band diagram on the P side is raised relative to the energy band diagram on the N side. Remember, the energy band diagram can be interpreted as an inverted potential diagram, which I mentioned before. Now, if the reverse bias is high enough, right, it is possible to raise the valence band edge of the P side above the conduction band edge on the N side. Now, when this happens, one of the three conditions is fulfilled. Why do I say that? If you look at the valence band on the P side, we have lots of valence electrons. If you look at the conduction band on the N side, there are many empty energy states in the conduction band. And the two are separated by a potential barrier. This potential barrier is essentially approximately the band gap of the semiconductor, right? Now, why do I say that? Now, classically, in order for a valence band electron to get to the N side, right, the valence band electron first would have to be excited to the conduction band of the P side before it can move to the N side. Right, so the conduction band of the semiconductor here actually serves as a potential barrier to the valence electron. Okay, now, how about the rest of the condition? Okay, so there is a tunneling barrier, right, that separates the valence electron from the empty energy states on the N side. Right, so that condition is also fulfilled, and we can actually ensure that the thickness of the barrier is small. In other words, we can have a very thin depletion region, that can be done by doping heavily the P and N side. I will come back to this point again later on. Now, thirdly, there is an electric field across the PN junction under reverse bias. And if you check the direction of the electric field is actually pointing from N to P, right? Or from the right to the left. In other words, the direction of the electric field actually favors the tunneling of the valence band electrons from the valence band on the P side to the empty conduction band on the N side. So the three conditions are fulfilled, and therefore Zener tunneling can happen under reverse bias condition. Now, if we make sure that the barrier is thin and the electric field is large, then the probability of tunneling can be increased very significantly, and therefore a large current can flow in a reverse bias PN junction. So that is the basic theory behind Zener breakdown. Now, Zener breakdown can only happen after a sufficiently large reverse bias is applied. How to understand this? If you look at the diagram on the left, which corresponds to an energy band diagram of a PN junction under a much smaller reverse bias. In this case, the P side band diagram is not raised very significantly above the N side band diagram. So one of the three conditions is not fulfilled. And essentially, if you look carefully, the valence electrons, right, on the P side have no energy states to tunnel to, right, on the N side, okay? Because if tunneling were to happen, the electron is actually tunneling into the band gap of the N side, where there are no energy states available. In other words, if we solve Schrödinger equation for this particular situation, there will be no real solution for the electron wave function on the N side. So in this case, quantum mechanical tunneling cannot happen, or Zener breakdown does not occur in this case when the reverse bias is too small. Okay, so what is the minimum reverse bias needed for quantum mechanical tunneling to happen? Well, it's quite easy to understand that. So let me go to one slide and show you that. Now you do not have this. You can take this down if you wish. Now, essentially, from the discussion just now, you should understand that quantum mechanical tunneling will first happen when the valence band on the P side becomes aligned to the conduction band on the N side. Because beyond this, in other words, when a larger reverse bias is applied, then the valence band on the P side can be raised above the conduction band HEC on the N side, right? So that is the minimum reverse bias for the onset of Zener breakdown or quantum mechanical tunneling to happen, when the valence band EV on the P side is just aligned with the conduction band EC on the N side. So what reverse bias voltage do we need to apply in order to achieve this? Now remember, in a PN junction under thermal equilibrium, the energy band diagram on the P side and the N side are already offset relative to each other due to the presence of the built-in voltage, QVBI, right? And in order to bring the EV on the P side to be aligned with the EC on the N side, the band diagram on the P side must shift up relative to the N side by an amount equal to the band gap energy. I think it's quite easy to understand this, right? So if I shift the band diagram on the P side upwards by an amount equal to the band gap energy, then the EV on the P side will get aligned with the EC on the N side. All right, but there is already a relative shift, as what I've just mentioned, due to the presence of the built-in voltage, and therefore the additional reverse bias voltage that we need to achieve this situation is simply EG minus away the built-in voltage. Keeping in mind that VA is negative under reverse bias condition. Okay, so this is theoretically the minimum reverse bias voltage needed to cause the onset of Zener breakdown. But however, at such a voltage, the current that flows through the junction may not be large because besides having to align the EV and the EC, there are two other conditions that must be fulfilled. The thickness of the tunneling barrier must be small, and the strength of the electric field probably should be large. And these two conditions may not be favorable when the reverse bias is too small. All right, so generally the Zener breakdown voltage is much larger than the theoretical value discussed here. Okay. All right, so with that, you understand. Yes?
Very bad, huh? Yeah, very bad.
Yes? Yeah, you wanna ask a question? Okay, so maybe you have accidentally turned on your mic. Okay, so let's continue. Okay, just to summarize before we move on. So Zener breakdown occurs when the applied reverse bias is such that it lowers the conduction band edge of the N region below the valence band edge of the P region. Or the other way around, if the reverse bias voltage is large enough to raise the valence band edge of the P side above the conduction band edge on the N side. Okay, so when this happens, electrons in the valence band of the P region could quantum mechanically tunnel to the empty states in the conduction band of the N region. All right, now if the reverse bias is too low, then the tunneling cannot happen because there are no empty states for the electrons to tunnel to. Okay, so we discussed that just now. Now the breakdown voltage or the Zener breakdown voltage can be changed by changing the doping concentration of the P and N region. Now, why is that the case? Now, you need to recall, right, the width of the space charge region, which essentially is the thickness of the tunneling barrier, depends on the doping concentration. If we dope the N and the P and the N side heavily, then the space charge width or the width of the depletion region will be small. Okay, so a small depletion region corresponds to a thin tunneling barrier, and that increases the probability of tunneling across the barrier. All right, now at the same time, doping the N and the P region heavily also increases the electric field at the PN junction. Now, if you recall, we discussed this before, right? So the maximum electric field occurs at the metallurgical junction and can be expressed like this, right? This was derived earlier. So essentially, when we increase the doping, the maximum electric field strength increases, and that favors the tunneling process, okay? So by doping the N and the P side heavily, right, essentially would make it easier for an electron to tunnel through the energy barrier. Okay, so when more quantum mechanical tunneling happens, a higher reverse leakage current can be obtained. Okay, so as mentioned, in practice, the desired breakdown voltage can be adjusted by varying the doping concentration of the P and N region. All right, so that's the concept behind Zener breakdown. Now, Zener breakdown is useful in a sense that the breakdown is not destructive. That's why the Zener breakdown can be exploited in circuit operation. Like, for example, in the voltage regulator that I mentioned earlier. Because when the voltage is removed, the diode recovers. And the next time when you apply the voltage, the diode breaks down again. right? So Zener breakdown is not destructive, and that's why it is useful. Now, the second breakdown is called the avalanche breakdown, right? So let's try to understand what causes avalanche breakdown to happen. Now, in contrast, avalanche breakdown is actually destructive in the sense that the diode is normally destroyed when avalanche breakdown happens. And because of that, the PN junction diode is never operated under avalanche breakdown. So let's try to understand what causes avalanche breakdown. Now, there are 2 points that you need to keep in mind. The first point is about impact ionization, which I will explain. Now, the second point is about the chain reaction that takes place after impact ionization starts to happen. Okay, so let's try to understand what is impact ionization. Now, essentially in the space charge region or the depletion region of a PN junction under reverse bias, there is a high electric field. So if there is an electron present in the space charge region, the electron can be accelerated to very high kinetic energy by the high electric field, making it highly energetic. Now, when this highly energetic electron collide with the lattice, it can transfer its excess kinetic energy to an electron that is participating in the covalent bonding between 2 silicon atoms, for example, as shown here. So this excess kinetic energy of the energetic electron can be transferred to one of the electrons in the covalent bond here, and thereby breaking the covalent bond. Or in other words, this electron can get excited to the conduction band of the semiconductor. Now, this process whereby an energetic carrier, electron or holes, creates additional electrons and holes, right, within the semiconductor is called impact ionization. Okay, so why is impact ionization important in avalanche breakdown? We will see later on, okay? All right, so impact ionization is a very important concept related to avalanche breakdown. So please try to understand what the concept is all about. Okay, so what happens after impact ionization? As you know, impact ionization creates additional electrons and holes. Remember when the bond here is broken and one of the electrons get liberated, we create a hole at the same time, right? Electron hole pair creation. Now, what happened actually after that is important because this electron and hole can in turn get accelerated, right, by the high electric field, causing further impact ionization. All right. So that is the important point that leads to the second process, chain reaction. Okay, so to illustrate this, let me bring you to the Venn diagram here. All right, so this is the Venn diagram of a reverse bias PN junction, right? Where, as you can see, the Venn diagram on the P side is significantly raised above that of the N side, right? Under a large reverse bias. Now, if there is an electron present within the space charge region, right, this electron can get accelerated to very high energy, right, by the high electric field that is present inside the space charge region. Now, when it gains high energy, it can create impact ionization, right, by imparting some of its excess kinetic energy to a valence band electron, thereby exciting it to the conduction band. So if you look at this arrow, right, it represents this electron gaining significant excess kinetic energy. At this point, impact ionization happens. So the excess energy is actually transferred to this valence electron, promoting it to the conduction band. Promoting it to the conduction band. And in the process, an electron hole pair is generated. Now, at this point, after impact ionization, you have 2 electrons and 1 hole. So there are 3 charge carriers now compared to the only one at the beginning. So the 2 electrons here can get in turn accelerated to very high energy by the high electric field, right? And they can also create impair ionization. So at this point, impair ionization happens, right? So the two electrons impart their excess energy to two valence band electron, promoting them to the conduction band. Right, so at this point, you have 1, 2, 3, 4, 5, 6 carriers. So as you can see, a chain reaction basically has taken place whereby one carrier has now produced many more charge carriers by impair ionization. It's a chain reaction because impair ionization creates more carriers and the generated carriers in turn create more carriers. So it gives rise to a chain reaction. Now, not to forget, the holes that are created, right, by the impair ionization can also get accelerated by the electric field to high energy, causing impair ionization, right? So this arrow here represents this hole being accelerated to very high kinetic energy, right? So at this point, this excess kinetic energy is imparted to another valence electron, causing the generation of electron-hole pairs. All right, so both the holes and electrons that are created by impair ionization, they themselves, all right, can create more charge carriers through further impair ionization. And this sets off a chain reaction, causing more and more charge carriers to be generated, and therefore the current can increase very rapidly. And when that happens, we say that the diode has experienced avalanche breakdown. Right, so they borrow the word avalanche from the snow mountain avalanche. Remember, in the on a snow mountain, the avalanche is actually usually triggered by a small snow particle at first, rolling down the snow mountain. So as the snow particle rolls down the snow mountain, it gains momentum. At the same time, its size also grows. Right, so along the way, if it hits an obstruction, it will break in. Well, the big snow particle will break into smaller snow particles, and each of them in turn roll down the mountain, right, creating more and more snow particles along the way. Okay, so this avalanche breakdown is the word avalanche is actually borrowed from the snow avalanche that happened on the snow mountain. Okay, right. So there are two important points here, as mentioned. One is the impair ionization process, and the other one is a chain reaction that kicks off after impair ionization has happened. Now, because of the chain reaction or a positive feedback electron-hole pair generation process, the current can increase very rapidly and uncontrollably, right, during avalanche breakdown. And because of this, there is no way to control avalanche breakdown once it happens, right? The current just keep increasing, and with a very high current flowing through the PN junction, heating will take place, and the temperature of the PN junction diode can increase very significantly once avalanche breakdown happens, leading to the destruction of the PN junction. Okay, so the avalanche breakdown process is actually destructive. Now, in comparison, the Zener breakdown process is not destructive because the current, although it can also be relatively large, all right, but this current is limited by the tunneling barrier. Okay, so there is no chain reaction process taking place during Zener breakdown, and therefore the current does not increase uncontrollably. Right, so this differentiates Zener breakdown from avalanche breakdown. And Zener breakdown is therefore non-destructive because the current flow through the breakdown diode is actually can be controlled. Okay. All right, now with this understanding, we can predict the breakdown voltage at which avalanche breakdown happens. All right. First of all, you should realize that the electric field must be large enough to accelerate the charges, the electrons and the holes to high kinetic energy before impair ionization can happen, right? So therefore, the onset of impair ionization would happen only after the electric field exceeds a certain critical value called the critical electric field, right? Which is a property of a given semiconductor, all right? So the critical electric field is the point at which significant impair ionization starts to take place within the semiconductor. Now for silicon, the critical electric field is typically around this value, 3 times 10 to the power 5 volt per centimeter. And it generally vary with the doping. Now, how to understand the variation of the critical electric field with doping? Remember, doping introduces impurity centers into the semiconductors, and due to impurity scattering, the mobility of the electrons and the holes actually decrease when the doping concentration is increased. Now, with a reduction in electron hole mobility, it is less likely for an electron or hole to gain significant kinetic energy, right, within a given electric field because it tends to suffer more scattering events. Scattering event is actually an event where the charged particle, electron or hole loses its energy. Okay, so with more scattering, due to more doping impurities, the heating effect or the process by which the charge carrier gain high kinetic energy is less favorable. Okay, so the critical electric field will tend to be higher when the doping concentration is increased. Okay, so with this understanding, we can try to estimate the breakdown voltage that correspond to avalanche breakdown. So recall that the maximum electric field within the semiconductor exists at the metallurgical junction and is given by this equation. All right, Xn is the width of the space charge region within the N site, and Xp is the width of the space charge region within the P site. Now we can use either one of these two expression here, right? Since the maximum electric field is continuous at the metallurgical junction. Now Xn and Xp are in turn given by these two expressions that can be shown, right? We actually did that much earlier already, okay? So let's just substitute Xn or Xp into the expression for the maximum electric field and then taking square of on both sides to remove the square root sign here. All right, we'll get expression for the maximum electric field square in this way, right? Now, what we can do is that since the parameter of interest here is actually the reverse bias voltage VA, so we can bring the voltage term to the left and the rest of the term to the right. And at this juncture, it is possible to make an approximation because the reverse bias generally is much higher than the built-in voltage. And if it gets 10 times or more higher, we can neglect the VBI term and keeping only the minus VA term. All right, and we can set minus VA to be VR, which is the reverse bias voltage. Okay, so the reverse bias voltage that corresponds to a certain maximum electric field at the metallurgical junction is given by this expression. Now, as mentioned earlier, avalanche breakdown happens when the maximum electric field starts to exceed the critical electric field. And therefore, the voltage at which the onset of avalanche breakdown happens can be estimated by equating the maximum electric field to the critical electric field of the semiconductor. So this is what we did next. Okay, so by equating Emax to EC. Now, EC here does not refer to the conduction band, but it refers to the critical electric field. Well, that corresponds to the onset of imperialization, all right? So once we equate Emax to EC, the reverse bias voltage corresponds to the breakdown voltage or the voltage at which avalanche breakdown happens. Okay, now if you look at this result here, the VBR depends on the doping term. It's not surprising because the maximum electric field in a PN junction is determined by the doping concentration of the P and N side. Okay, so let's do one simple calculation exercise to determine the maximum or the breakdown voltage that corresponds to the avalanche breakdown. Okay, so this PN junction is given by doping concentration on the N side and the P side, which are equal. Okay, so you're asked to calculate the avalanche breakdown voltage, given that the critical electric field is 3.5 times 10 to the power 5 volt per centimeter. All right, so the calculation is very simple, but just take note of the result. All right, the order of magnitude of the avalanche breakdown voltage is typically in several tens of volts. It can go up to several hundreds of volts as well. It all depends on the doping concentration. Okay. Now, in comparison, the Zener breakdown voltage is much lower. Remember, we discussed the theoretical Zener breakdown voltage is actually very small, right? But then, of course, at that point in time, the tunneling current may not be very significant, and generally, significant tunneling current only can be observed a couple of volts higher than the theoretical value. Okay, so the Zener breakdown voltage is usually in the range of about 5 to 20 volts. In fact, it's usually 5 to 10 volts. Okay, so it's smaller compared to the avalanche breakdown voltage, which can range from several tens to several hundreds of volts. All right. Now in question 2, in example 2, all right, you're asked to design an N plus P abrupt junction to achieve a breakdown voltage of 100 volts, given the critical electric field. Now, N plus P is a junction where the doping on the N side is much higher than the doping on the P side, at least 10 times or even higher. Okay, so for an N plus P junction, a possible approximation can be made. Since ND is at least 10 times or more higher than NA. Now, if you look at the expression for the breakdown voltage, you have this NA term, ND term, right? So one of them is much bigger than the other. In this case, ND is much bigger than NA. So we can approximate by saying that NA can be considered negligible compared to ND. Now, if you do that, then the expression for VBR will simplify into this form. Okay, so if you neglect NA, the ND in the numerator and the denominator will cancel out, and the simplified expression for the breakdown voltage can be obtained. So in this exercise, we want the breakdown voltage to be 100 volts. Okay, and given the critical electric field, we can therefore determine the required doping concentration on the P side, which is 3.96 times 10 to the power 5 for this example. All right, so we can fulfill this condition where the breakdown voltage is 100 volts so long as we dope the P side to this value, and then we dope the N side much higher than this value, 10 times or more higher than this value. Okay, then the N plus P junction diode that you create will have a breakdown voltage of about 100 volts. All right, so that's how the PN junction can be designed to achieve a certain breakdown voltage. Okay. Now there are two comments here, right, that you can take note of. The avalanche breakdown voltage of a one-sided PN junction. Now, one-sided PN junction is another name given to a PN junction whereby the doping on one side is doped much higher than the doping on the other side. Okay, so the avalanche breakdown voltage of a one-sided PN junction is controlled by the doping concentration of the lowly doped side. Right? You can see this easily from this approximated expression here, whereby VBR is actually inversely proportional to NA, which is the doping concentration of the lowly doped side in this example. Okay, all right. Which is mentioned here. All right. Okay, so with that, the discussion on the reverse breakdown of the PN junction is complete. So to summarize, there are two possible breakdown mechanisms. One is the Zener breakdown. The other one is the avalanche breakdown. All right. Now, Zener breakdown is non-destructive because the current flowing through the breakdown diode is controllable. There is no chain reaction that causes the current to increase uncontrollably. right? Because in Zener breakdown, the current flowing is limited by the tunneling barrier. On the other hand, in avalanche breakdown, which is destructive because the current that flows during avalanche breakdown can increase very significantly and uncontrollably due to the onset of impermeabilization and a chain reaction process that causes more and more carriers to be generated through impermeabilization. Okay, so Zener breakdown therefore has a lot of practical value. Well, as mentioned, in circuits, some diodes are designed to operate as Zener breakdown diodes, whereas avalanche breakdown is never considered to be useful due to its destructive process. Okay, so with that, the understanding on the IV behavior of the diode should be more complete, right? And you should understand why the diode eventually will also suffer electrical breakdown when the reverse bias is large enough. Okay, now, so the first topic is done. At this point, any questions?
Hi, Prof. Two questions. So does that mean all diodes will go through Zener breakdown before going into avalanche breakdown?
Okay, right. So your question is, you asked this question probably is because you saw this one. So your question is, does that mean all diode will go through Zener breakdown before avalanche breakdown, which means that avalanche breakdown is not relevant because all diode will eventually break down earlier due to Zener breakdown. Now, it is not necessarily the case, although theoretically speaking, like what we have mentioned before, Zener breakdown theoretically happens when the valence band on the P side get raised above the conduction band edge on the N side. However, even when this situation exists, the current that flows through the junction can still be very small, right? The reason is because the doping concentration may not have been optimized to give you a narrow depletion region or a narrow tunneling barrier. And because of that, the electric field may not be that high as well. So although quantum mechanical tunneling can happen in principle, the probability of electron tunneling to the N side is actually very small. The current actually becomes very small if the doping concentration are not optimized. Not optimized means they are not made to be very high, all right? So in that case, the diode does not register a significant increase in the current, all right, when this situation exists. Now, if you continue to increase the reverse bias voltage, then the depletion region will get wider and wider. Remember, under reverse bias, the depletion region actually gets wider and wider. So when that happens, the tunneling, the width of the tunneling barrier is actually increasing as a function of reverse bias voltage. So that actually suppresses further Zener tunneling. But however, as you increase the reverse bias voltage, the electric field gets higher and higher. All right. So when the electric field exceeds the critical field, then avalanche breakdown will happen. All right. So to summarize, a diode can undergo Zener breakdown provided the doping of the P and N are made very high, right? To give a very small tunneling barrier. Okay, this is important. All right. Now, if this is not done, then although tunneling can happen in principle, the probability is actually very, very low. Okay, so if you keep increasing the reverse bias, you're actually increasing the depletion region, so that will actually reduce the tunneling barrier even more. All right, so under those situations, avalanche breakdown would happen. Okay, all right.
Okay, thank you, Prof.
All right, any other questions?
Hi, Prof.
Yes.
Could I know why the Fermi level is not aligned when the reverse breakdown voltage is high?
Okay, your question is related to this diagram, I believe. So why the Fermi levels are not aligned when the reverse bias voltage is high? Is
Yes.
that your question?
Yes.
Okay, now you have to understand that the alignment of the Fermi levels only applies under thermal equilibrium. Okay, now when you apply an external voltage across the PN junction, the alignment of the Fermi level no longer applies. In fact, they split into two levels like this. Like for example, in this diagram here, which is under reverse bias voltage, right? The Fermi level on the P side is raised above the Fermi level on the N side. And how much is it raised above the Fermi level on the N side? It is equal to the magnitude of the applied voltage. All right, because the moment you apply external voltage to the PN junction, the PN junction goes into non-equilibrium. So in non-equilibrium, the Fermi levels do not align as there is charge transfer across the junction. The Fermi levels are only aligned when under thermal equilibrium. While it is not shown here, this is still not under thermal equilibrium. In fact, I think I have a diagram just now. Right, so under thermal equilibrium, the Fermi level is on both sides are aligned. Okay, because there is no net transfer of charge across the junction under thermal equilibrium. Okay.
Yeah, thank you.
Hi, Professor. Can I ask, with respect to the avalanche breakdown, you said that the holes can also cause like more generation because they move faster. How would you visualize that? Because the hole
Okay,
itself
so-
is not like a actual piece of metal.
All right. Now, to understand this, you need to realize that the movement of holes can be interpreted as the opposite movement of the valence band electrons. You are right, hole is actually an empty energy state. Strictly speaking, it doesn't move. But however, its movement can be visualized to be equivalent to the opposite movement of the valence band electron. Okay, to help you better visualize that, you can look at this diagram here. Right, so upon impaired ionization, an electron hole pair is created. So there's a hole here, which is an empty energy state here. So how can this move? Now, for example, this valence electron here can hop on to occupy these empty energy states here. And when this valence electron moves from right to left, the hole can be visualized as having moved from left to right. Right, so this is how we visualize the movement of holes in the valence band. It's actually opposite to the movement of the valence electron. Actually, strictly speaking, it is the valence electrons that are moving, not the holes. Okay, all right. So since this is the case, therefore, holes in principle can also be accelerated to very high energy, right? Because it's valence electron that are moving. So the valence electron within the valence band can also be accelerated to high energy, all right, causing impaired ionization. So with that, I think it should be easier to visualize how the holes can be accelerated to high energy and causing impaired ionization.
So the impact ionization is caused by the charge and not by the mass of the impact, like the mass of the two objects like impacting.
The impaired ionization is caused by the charge, not by the mass. Okay, now the impaired ionization is caused by an energetic carrier of a certain mass colliding onto another carrier, thereby in the process, the excess energy of the energetic carrier is transferred to the less energetic carrier. So it is still a kind of a, well, I wouldn't say it is caused by the charge, right? It's still caused by the mass of the particle, right? Because it's the mass that gives it some kinetic energy, right? So with that kinetic energy, when it becomes energetic with high kinetic energy, then it can pass on to another less energetic carrier. You can think of like two billiard balls colliding with each other, right? One of them is stationary. So imagine this a valence band electron, right? And the other one is actually highly energetic, is actually moving at high speed. So as they collide, right? So some of the excess energy from the fast-moving particle is transferred to the stationary one, causing the stationary one to be dislodged, and it can move also as well, right? Is that okay? Does that answer your question?
Yeah, thank you.
Okay, all right. So if you have no further question, then I'll move on to the second topic, which is on junction and storage capacitances. Now, as mentioned before, now let me just bring up the slide first. As mentioned, the concept of capacitance is actually not taught in your H2 physics. So in order to facilitate later discussion, I have prepared some preliminary material, right, on capacitance. So with that discussion, hopefully it gives you some background knowledge on the capacitance itself. All right. Okay, let me bring up the slides. Okay, now I call it capacitor 101. So basically, it's a very short discussion, hoping to build some foundation on this concept. It is not exhaustive, right? So there are many things that I have left out. I have only focused on the essential parts. Okay, so what is a capacitor? Now, a capacitor is one of the four very important circuit components. Okay, remember you have the resistor, you have the inductor, and capacitor is one of the four, and the fourth one is actually the memristor. Right, the memristor is less well known because it was only discovered very recently. All right, the concept behind memristor was actually proposed in the 1970s, and the first practical device, memristor, a real device, actually was realized only in the late 2000s. So what is a memristor? A memristor is a memory resistor, right, which can have its resistance change, and it can memorize, it can remember the change in the resistance. Right, so with these four circuit components, any kind of circuit can be built, basically. All right, so coming back to capacitor, capacitor is therefore one of the four very basic circuit components. So what does a capacitor do? A capacitor stores charge, and the amount of charge it stores can be changed by the voltage applied across the capacitor. Now, the simplest form of capacitor is the parallel plate capacitor, right, shown on the diagram on the left here. Essentially, a parallel plate capacitor has two plates separated by a certain distance d. Now, if you ground one plate and apply a voltage to the other plate, imagine you apply a positive voltage to the other plate. So positive charges will be deposited on the upper plate, and the positive charges will induce an equal amount of negative charges on the bottom plate. Now imagine you change the voltage applied to the top plate by a certain amount delta V, and assuming delta V is positive, that means overall the voltage applied to the top plate is more positive than before, right? So you deposit more positive charges on the top plate, and these additional positive charges will be balanced by additional negative charges they induce on the bottom plate. All right, so essentially this serves as a capacitor because this arrangement of the two plates separated by a certain distance can store charge, and the charge stored can be changed by changing the voltage across the two plates. So that's how the concept of capacitance is defined, right? So capacitance, which is an important property of the capacitor, is a measure of the capability of the capacitor in storing charge. And therefore, it is defined as dq over dV, the change in the charge stored for a given change in the voltage. So if the change in the charge stored is large, for a given change in the voltage, then the capacitance is large. Okay, all right. We can later show that the capacitance of this parallel plate capacitor can be derived and shown to be of this expression here, right? Where epsilon r is called the relative permittivity of the medium that separates the two plates. I will explain a bit on the concept of permittivity later on, right? And epsilon naught is the permittivity of free space, and A is the area of the plates, okay? And D is the separation of the two plates. So the capacitance is inversely proportional to the separation of the two plates. So when D increases, the capacitance decreases. And it's easy to understand why that is the case, because when you increase the distance between the two plates for a given change in the voltage, then the change in the electric field will be small because of the larger distance. And since the change in the electric field is small, the change in the charge will be small. Right, so with a smaller delta Q for a given delta V, then the capacitance actually becomes smaller. Okay, so that can be easily understood, right? So next, I will try to derive this expression, right? Now, before that, just a point here for you to take note. Now, since capacitance is defined as dq over dV, if we invoke the product rule, all right, we can express dq over dV as dq over dt times dt over dV. Okay, now as you know, dq over dt is actually current, right? Current is defined as the rate of change of charge with respect to time. And if we bring dt over dV to the right, we can write this expression as I, which is a current, dq over dt, as C times dV over dt. Okay, dV over dt represents the rate of change of voltage across the capacitor, right? When multiplied by the capacitance, will give you the current that flows in the capacitor. Now, some of you may ask, what is this current? Does it flow across the plate? No, the current does not flow across the plate. That's why people call this the displacement current. This is called the displacement current, meaning that whenever there is a change in the voltage across the two plates, charges must be either transported to the plate or transported away from the plate in order to cause the change in the charge. And this transportation of charges that happen when the voltage is changed is called the displacement current. Okay? Now, I is C dV dt. Now, this equation itself has an important point in the sense that in a capacitor, the voltage across the capacitor cannot change indefinitely, or in other words, dV dt must be finite. It cannot be infinite, right? In other words, if dV dt is infinite, for a given capacitance, your current will be infinite, which is non-physical. Okay, so it's important for you to remember that the voltage across the capacitor cannot change immediately. All right, so this is an important point to keep in mind, because if that is the case, if dV dt is very large or infinite, then the current is infinite, which is not physical. Okay. So let's try to derive this expression in order to do that, I want to introduce something which is also of fundamental importance, and this is called Gauss law. Gauss law is a very important fundamental law in the subject on electrostatics. Okay, it basically relates the electric field to the charge located in the particular region in space. All right, now imagine, just for the example, if I have some positive charges here, plus Q, all right? So there will be electric field emanating from these positive charges, and I can relate the electric field at a certain distance away from the charge to the amount of charge stored, or to the amount of charge present here, okay, using Gauss law. So Gauss law says that if you draw any surface enclosing the charge here, and if you take the dot product of the electric field and the surface vector of the surface of this surface that you have drawn, okay, and then you integrate this throughout the entire surface, or you sum them up throughout the entire surface, which is what integration basically means. All right, you sum this dot product up over the entire Gaussian surface. Then on the right side, you have Q divided by the permittivity of the medium where the charges are present. Okay, epsilon r is a relative permittivity, and epsilon naught is the permittivity of free space. Okay, this is Gauss law. It's very useful because if we know the charge, and if we can draw a Gaussian surface that help us evaluate this integral, right, then we can easily find the electric field, right, due to the presence of the charges, okay, which is what I'm going to show you next for the parallel plate capacitor. All right. So let's apply Gauss law to the parallel plate capacitor. Now, Gauss law in principle works for any shape of the Gaussian surface. Okay, right? But of course, we do not want to make life difficult for ourselves. We will always choose the Gaussian surface that allow us to evaluate this integral most conveniently. So in the parallel plate capacitor, this would be a suitable Gaussian surface, a rectangular surface like this. So the one side of the rectangular surface is located in between the two plates here, all right? And the rest are shown here, okay? Now for this particular example, we will expect the electric field to exist only between the two plates. There is no electric field outside the plate, and there is no electric field so-called outside the plate, basically, okay? So with this understanding, all right, we can easily evaluate this integral. So if you look at this integral, it is only non-zero at this surface. Okay. Now at this surface of the Gaussian surface here, at this part of the Gaussian surface here, it is zero because there is no electric field. Now at the side, right, of the Gaussian surface, the contribution to this integral is also zero. Although there can be electric field along the side of the Gaussian surface, but if you take the dot product with the surface vector, actually the result is zero because the two vectors are perpendicular to each other. Remember, the surface vector is actually vector pointing outwards from the surface perpendicular to the surface. Okay, all right. So with this understanding, so the integral only has non-zero values on this part of the Gaussian surface. And if the medium that separates the two plates is homogeneous, is uniform, then we will expect the electric field to be constant throughout the region between the two plates. Since electric field is a constant, you can pull it out of the integral, right? And the integration of ds is simply to find the area of the Gaussian surface, right? So since this is the only part where there is non-zero contribution to the integral, this area of the Gaussian surface is equal to the area of the plate, A. Okay, so this is how we can apply Gauss's law to this simple example of a parallel plate capacitor. Now, since the electric field is V over D, V is the voltage applied to the plate, D is the separation between the two plates, right? And from here, right, we can therefore differentiate both sides of the equation. So we can differentiate this equation with respect to Q. So I have dV here and I have dQ here. And since capacitance is defined as dQ over dV, therefore we can show that the capacitance of this parallel plate is actually the permittivity times the area of the plate divided by the separation D. Okay, all right, so this is just one simple application example of Gauss law. You can apply Gauss law to other kinds of situation. In fact, we did that earlier to the PN junction in case you didn't realize it, but we did that in the form of Poisson equation. Okay, Poisson equation is actually the differential form of Gauss's law, right? You can easily see that. Okay, all right. Now, the concept of parallel plate capacitor is useful because later on through the discussion of the PN junction capacitance, you will realize that the behavior of the PN junction capacitance is quite similar to the parallel plate capacitor. Okay. Okay, so before I leave this short discussion, I just want to say something about permittivity in case some of you are not very clear what this is all about and how does it affect the capacitance that we are looking at. So the permittivity can be defined as the resistance that is encountered when forming an electric field in a particular medium, or the amount of charge needed to generate 1 unit of electric flux in the medium. Now the alternative definition here actually stems right out of Gauss's law. So if you look at Gauss' law, okay, if you consider per unit electric flux, that means on the left side of this equation, it has a value of 1. Okay, so if that's the case, then the permittivity, if you bring it over to the left side, the permittivity of the medium is essentially the amount of charge Q that you need to have in order to create 1 unit of electric flux. Now, more intuitively, the definition of the permittivity is more intuitive if you think of it as resistance encountered when forming an electric field in a particular medium. Now, this can be illustrated using this diagram here. Now, in any medium, whether semiconductor or something else, there is always, or it is always possible for an applied electric field to result in polarization of the medium. Now, what does that mean? Okay, in some materials, we have dipoles. Right. For example, if you take the example of a compound semiconductor such as gallium arsenide, since gallium and arsenic have different electronegativity, so if you form a compound with 2 elements of different electronegativity, so there will be non-equal sharing of charge. Right, because one element tends to like electrons more than the other element. So as a result of that, as a result of this difference in electronegativity, the gallium arsenide molecule is actually polar. In other words, one part of the molecule is actually slightly positive with respect to the other. Now, in the absence of electric field, the dipoles are randomly oriented. Okay, so if we apply an electric field across the medium, right, the electric field can cause alignment of the dipole to happen like this. For example, if you apply a positive voltage to the top plate and then ground the bottom plate, so the electric field points, and you apply a positive voltage to the top plate, the electric field will point downwards like this, reorientating the dipole in this direction consistently. Okay, where the negative end of the dipole actually points towards the positive plate, and the positive end points towards the negative plate. Now, in the dipole, there is an electric field that points from the positive end of the dipole to the negative end. Essentially, when the dipole is oriented like this, all right, there is an electric field that tends to oppose the applied field. Okay, and if the material is very polarizable, in other words, it has a high concentration of dipoles, and right, so what happens is that there will be a strong resistance, all right, presented by the dipole to the applied electric field, causing the net electric field to be smaller than the applied electric field. So that's why permittivity is defined as the resistance encountered when trying to form an electric field in a particular medium. Okay, so this is the concept of permittivity, right? So how does it apply in our case of a parallel plate capacitor? I will come to that shortly. Before that, I just want to also mention that it is also possible for dipole to exist even in an element like silicon. Now, as you know, silicon is an element with only one particular atom. So how can a dipole exist? Now, in the presence of an electric field, right, the electric field can cause relative movement between the electron cloud and the nucleus. As you know, the nucleus is positive, the electron cloud is negative. So if you apply an electric field in a particular direction, it will tend to shift the electron cloud in a particular direction relative to the nucleus. And this can cause instantaneous polarization of the material. Okay, so a material need not have dipole molecules to begin with in order for it to be polarized. It can be instantaneously polarized in the presence of an electric field due to the relative movement of the electron cloud and the nucleus. Okay, so how does this polarization of the dielectric apply in our case? Now, that is the reason why we need to include the relative permittivity here. Now, imagine the region that separates the two plates is not vacuum, okay, but it is made out of some material that is polarizable. In other words, during the application of the electric field, external electric field, there will be alignment of the dipole, and the dipole themselves will create an electric field that opposes the applied field. Okay, so as a result of the polarization of the medium, okay, so the net electric field across the two plates will be smaller. All right, so from Gauss's law, you can see, so with a smaller net electric field, the integral will be smaller, right? And therefore, to represent this result, we include an additional number here, and this number is called the relative permittivity of the medium. So overall, the expression on the right side is also reduced if this number is bigger than 1. Okay, usually this number is bigger than 1, right? 1 is for vacuum, right? Epsilon naught, right? So if you have a material in between the two plates, then epsilon r will be bigger than 1. So reducing the value on the right side of Gauss's law, and we should make it consistent to the fact that the net electric field across the medium is actually reduced due to the polarization of the medium. Okay, so this explains the significance of this relative permittivity term here. All right, okay. Okay, I think with that, I hope it gives you enough background to understand what we are going to discuss next on the junction capacitance. Okay, so all right, so now the time is about 5:25. So we'll go for a short break of 10 minutes at this point. So please come back at 5:35. All right, we will resume the discussion on the PN junction capacitances. Okay, in the meantime, you can still ask questions. Right. Okay, all right, guys, let's resume the discussion. Right, so let me bring up the slides on capacitance. Okay, before that, just a quick sound check, right? Make sure that things didn't change. All right, if you cannot hear me, please let me know. Okay, so the next hour we'll focus on the PN junction capacitances. So if you look at this diagram, there are three very well-known basic circuit components, right? Resistor, inductor, and capacitor. Okay, so the basic property of a capacitor is charge storage, right? So stores charge. Okay, so now why is the concept of capacitance relevant to the PN junction? The reason is very simple. A PN junction stores charge, and the amount of charges it stores can be varied according to the voltage applied across the PN junction. All right, we'll come to the point of charge storage later on. All right, in fact, there are two different types of charges that can be stored at a PN junction. So that gives rise to two kinds of capacitances. The first one is the junction capacitance, or sometimes people call it the transition capacitance. And the other type is called the charge storage capacitance or the diffusion capacitance. Later on, we will discuss in detail each type of capacitance and examine the origin behind their existence. All right. Now, in a real diode, such as a practical diode, the two capacitances play a very important role in the transient response of the diode. Right, I will end the discussion with an example on how the capacitances can affect the transient response of the diode, in particular the turning off and turning on speed of the diode. So we usually model a real or a practical PN junction by connecting the two capacitances across the PN junction like this. Okay. Now, in an ideal PN junction, we can neglect the two capacitances. Of course, this assumption is not strictly valid. Right. Now, as you will later see, the junction capacitance has physical characteristics similar to a parallel plate capacitor. All right, so keep in mind what we have discussed for the parallel plate capacitor, especially the equation that we get for the junction capacitance is in fact identical to that of a parallel plate capacitor. All right. Now, the other type of capacitance, it's the storage capacitance, is also related to the charge storing property of the PN junction, but it is not identical to that of a parallel plate capacitance. Okay. Now, as what I told you earlier, right? Capacitance is present, or capacitive effect is present in any device, not only a semiconductor device, but in fact in any device. If a small change in the applied voltage across the device result in a change in some charge stored. All right, so the definition of capacitance is actually dQ over dV. Okay. Now, in the special case of a parallel plate capacitor, Q is proportional to V. All right, if you do not understand this or you have forgotten this, in fact, we saw the equation that relates Q to V earlier. You can refer back to the deck of slides on the capacitor 101. And you will see that in the parallel plate capacitor, the amount of charge stored on the plate is actually proportional to the voltage applied. Now, since that is the case, right, we can easily show that the parallel plate capacitance of, the capacitance of a parallel plate capacitor can be written as Q over V, where Q is the charge stored and V is the voltage across the capacitor. Now, at this point, a word of caution, Q over V cannot be used as the general definition for capacitance, and it is only valid if you are only looking at a parallel plate capacitor. In other words, for any general capacitor, the definition for capacitance is not Q over V. In fact, the former one should be dQ over dV. Okay? Only in the rare case where the Q is proportional to V, then we can write capacitance as Q over V. Please keep that in mind. Now, later on, you'll see that as we vary the voltage across the PN junction, the two types of charges stored at the PN junction can be changed. And I think most of you will have guessed by now that one of the two types of charges, one of them is actually the space charge. Okay, then what is the other type? Right, we'll come to that shortly. Now, as far as the change in the space charge is concerned, the capacitance is called the junction capacitance, which is defined as dQj over dV. Now, for the other type of charge stored, we can apply the same definition. So the storage capacitance is defined as dQs over dV. Okay. Now, why is junction capacitances important? Because as what I mentioned earlier, the voltage across the PN junction cannot change instantaneously. In other words, dV over dt, the rate of change of the voltage across the PN junction cannot be infinite. Okay, because that will lead to a non-physical outcome where the displacement current is infinitely large, which is not possible. Okay, so because of that, because of the presence of these capacitances, the dV dt, or the voltage across the PN junction, cannot change instantaneously with respect to time. And as a result, you know, the capacitances will introduce delay, right, in the switching response or the transient response of the PN junction, because time is needed to charge or discharge the capacitances in response to a change in the voltage applied across it. Okay, yeah, this is what I just mentioned. So this delay, right, time that is needed to charge or discharge the capacitances in response to the change in the voltage, right, can be understood as the amount of time that is required for a displacement current to flow in order to change the amount of charges stored. Right, charges need to be transported away or to the PN junction to change the amount of charge stored at the PN junction. Okay. So now let's look at each of the two capacitances closely. So let's begin with the junction capacitance. Now, by now you know that if we change the bias voltage across the PN junction, the width of the space charge region or the depletion width will change. All right, I hope you remember why that is the case. All right, for example, in the forward bias case, the applied electric field opposes the Ewing field, and the net field is smaller than the Ewing field. And because of the reduction in the electric field, we need smaller amount of space charge to support this smaller electric field, and therefore the width of the space charge region is reduced under forward bias. Okay. With that, I hope you can recall clearly why the width of the space charge region will have to increase under reverse bias. Okay, so what is the amount of space charge stored at the PN junction? Right, we can express it like this. Right, you can look at the P side. If you take QNA, which is the space charge density on the P side, multiply it with the volume of the space charge region, A times XP gives me the volume of the space charge region on the P side. A is the cross-sectional area, XP is the width of the depletion region on the P side. All right, so taking the product of the space charge density and the volume of the depletion region gives me the amount of space charge stored on the P side, which must equal to the amount of space charge stored on the N side by neutrality of space charge. Okay. Now XP and XN are in turn can be related to the doping concentration and the voltage applied. Okay, we'll come to that shortly. So under forward bias, W decreases and QJ decreases, whereas the opposite happens under reverse bias. So as a result of the change in the space charge stored at the junction in response to a change in the voltage applied across the PN junction, there is a capacitive effect, right? And this capacitive effect, people call it the junction capacitive effect or the junction capacitance. Okay, all right. Now, later on, as we proceed with the mathematical derivation, you will realize that in the case of a PN junction capacitance, the amount of space charge stored is not proportional to V. In fact, it is a nonlinear dependence on the voltage, right? You will soon see that clearly. So the ratio of Q over V cannot be used to determine or to define Cj. All right, remember I told you earlier here, okay? Here. All right, so please never define capacitance in general in this manner. All right, this is wrong in general, and it is only applicable to unique cases where, such as a parallel plate capacitor, where the charge is proportional, charge stored Q is proportional to the voltage V. Okay, so let's proceed with the mathematical derivation for Cj. Okay, I will come back to this slide later on. All right, so I'll KIV this for now. So let's move on. All right, Xn and Xp are in turn related to, or can be related to, the depletion with total depletion with W in this manner. Now, these two expressions can be obtained by solving the two equations, if you still remember. One of them is the space charge neutrality equation, and the other one is just a simple geometrical statement about Xn and Xp adding together to give you the total depletion width. So by solving these two set of simultaneous equations, you can obtain Xn and Xp in terms of W. And W, the depletion width, is in turn can be related to the voltage applied across the PN junction and the rest of the doping terms and the built-in voltage according to this expression. Epsilon is the permittivity of the semiconductor. Okay. Now, with that, we can use either Xn or Xp. So in this example here, I think I have chosen to use Xn. Right? Okay. Actually, we can't tell, right? Because the two are equal. Okay, so using either one of them, right, you should arrive at this expression here, right? After you put in W, right, and simplifying it further, right, you can cancel out certain terms, right, and the final expression for Qj is as shown here. All right, now at this point, just to note, as what I mentioned earlier, the amount of charge stored Q, space charge stored Q, or Qj, is not directly proportional to V. In fact, it has a square root dependence on the V. Okay, so because of that, I cannot just define the capacitance or the junction capacitance as Qj over V. That is wrong. So in order to obtain the expression for Cj, I need to differentiate Qj with respect to V. All right. So that is the definition, the formal definition for Cj. Now, since V0 is a constant, right, we can write dQj over dV as dQj over d bracket V0 minus V. Because V0 is a constant, upon differentiation, it will go to 0. Okay, so with that, you can easily differentiate the Qj expression with respect to V0 minus V instead of V, right? Well, it doesn't matter actually, it makes not much of a difference. You can also differentiate with respect to V, right? So equivalently, we can also differentiate Qj with respect to V0 minus V since V0 is a constant. And the final result that you get will be shown here. Okay, so this is the equation for the junction capacitance. All right, notice that the Cj is voltage dependent. Now, this is a very big difference compared to the simple parallel plate capacitor, which is constant irrespective of the voltage applied across the two plates. Okay, on the other hand, the junction capacitance is actually voltage dependent. I will come to this point later on, why that is the case. Okay, and since the rest of the terms are constant, for example, like the cross-sectional area A, the permittivity, the charge Q, the doping terms are usually fixed. Therefore, we can say that Cj is proportional to the inverse of the square root of V0 minus V. All right. Now, moving further, we can rearrange some of the terms here. So how do I do that? Okay, now remember W is given by this expression. Now, there are certain terms that are similar between this expression for Cj and the W term, which is shown here. So after some manipulation, we can actually show that Cj can be expressed equivalently as epsilon A over W. All right. To do that, what you can do is to divide this expression, this Cj expression, which is here by W, and multiply it by W in the numerator, and you will be able to cancel out some terms. Okay, when you do that, right? You can try that algebraically by yourself. Now, this result is is surprising at first. If you recall what is the expression for the parallel plate capacitance, it is also epsilon, the permittivity of the medium separating the two plates, multiplied by A, which is the area of the plate, divided by the distance between the two plates. Right, that is the expression for the parallel plate capacitance. So in this case, the Cj expression has identical form. Right, it's epsilon times the cross-sectional area A of the diode divided by W. Well, W represents some distance, right? So it's very similar to that of a parallel plate. Okay, so W in fact can be regarded as the separation between two plates inside the PN junction. So how do we make sense of this thing? Okay, let me go back to this slide here. Okay, let me go back to this slide here and try to make sense of the result that we have just obtained. In other words, the junction capacitance is epsilon A over W. And W, if you compare this expression to that of a parallel plate capacitor, W seems to suggest that it is representing some separation between two parallel plates present inside the PN junction. Okay, how does that work out? Now, look at this diagram here. Okay, so this is the metallurgical junction. M denotes the metallurgical junction. So on this side is the P, on this side is the N. How do I know that? Because the space charge is negative on the P side and is positive on the N side. So the vertical axis represents the space charge density, which is actually the doping density. Okay, right? Now imagine there is already a bias applied to the PN junction. So the PN junction actually stores some amount of space charge, positive on the N and negative on the P. And the amount of space charge stored is represented by Qj, corresponding to the voltage you apply. All right. For the convenience of discussion, just assume that this is a reverse bias voltage, although this assumption is not necessary. All right, so just assume that this is a reverse bias voltage, so there is some space charge stored Qj. Now imagine now you increase the reverse bias slightly by an amount dV. All right, so you're making the PN junction slightly more reverse bias by increasing the reverse bias by a small amount dV or delta V. So because of that, the depletion wave will widen slightly, right? And this widening of the depletion wave is necessary to account for the change in the electric field across the PN junction due to the slightly more reverse bias voltage that you're applying. Okay, so essentially the space charge wave has to expand, creating more space charge to support the greater reverse bias voltage. Right, so there'll be more space charge, more positive space charge needed on the N side, which must be balanced by the more negative space charge needed on the P side. Now, if you look at it carefully at this point, you can try to visualize as though there are two parallel plates, right? One is a positive plate, okay, denoting a certain amount of change of the positive space charge on the N side. And there is another plate, which is a negative plate, containing a certain amount of change of the space charge on the P side. Okay, And these two plates are separated by a distance of W. All right, so with this discussion, I hope you can try to visualize that why, in the end, the expression that we get for CJ is similar to that of a parallel plate capacitor. Because during the change in the voltage applied across the PN junction, the change in the space charge only happens at the edges of the depletion region. All right, positive space charge change happens here at the edge of the space charge region on the N side, and the negative space charge change happens here at the edge of the depletion region on the P side. Okay, so as though there are two parallel plates, one is a positive plate, the other one is a negative plate, and these two plates are separated by a distance of W. Okay, so with this, it's easy to see why the expression for CJ corresponds to that of the parallel plate capacitor. But although this is identical to the parallel plate capacitor, but there are differences as well. One of the major differences is that the junction capacitance is not constant, but it varies with the voltage you apply across the PN junction. Now, how does this work out? Essentially, when you change the voltage across the PN junction, you change the width of the depletion region, and as a result of the change in the width of the depletion region, you can think of it like this: the separation between the positive and the negative plates would be changed according to the voltage you apply across the PN junction. And as a result of that, the capacitance value is not constant, but it varies with the voltage across the PN junction. So this is a major difference between the junction capacitance and the parallel plate capacitance, although the two expressions are almost identical. Okay. Now, why does the capacitance decrease when you apply a reverse bias, and when you increase the reverse bias, it continues to decrease? And why does the junction capacitance increase when you apply a forward bias, and it continues to increase as you increase the forward bias? Now, one simple way to understand this is that as you increase the forward bias, for example, the depletion width narrows down. And for a given change in the voltage, the change in the space charge at the edges of the depletion region will be greater. Because for a given change in the voltage and a smaller W, the change in electric field across the space charge region will be higher, corresponding to a greater change in the space charge at the edges of the depletion region. So since the change in the space charge is larger for a given change in the voltage, then the junction capacitance increases. On the other hand, if you increase the reverse bias of the PN junction, right, the depletion wave widens. So for a given change in the voltage, the change in electric field across the space charge region is smaller, right, corresponding to a smaller change in the amount of space charge at the two edges, giving rise to a smaller capacitance. Okay, so the junction capacitance is not fixed, but it is a function of the voltage, which essentially changes the width of the depletion region, which can be regarded to be the separation between two parallel plates of charges within the PN junction. Okay, so with that, I hope you have a clear idea what junction capacitance is. Right. Okay, just one more slide. Now this is a repeated point. Basically, when we change the bias across the PN junction, why is the junction capacitance important? Because it takes time for the majority carrier to respond, to either expose a larger space charge region under reverse bias or to reduce the space charge region under forward bias. Okay, so a finite time is needed for the charge to respond, to change the amount of space charge stored. And therefore, the junction capacitance creates a delay in the response of the PN junction to externally changing electrical signal. Okay. It is sometimes more convenient if we express CJ in terms of CJ naught. So what is CJ naught? CJ naught is actually the junction capacitance at 0 bias, or in other words, at VA equals to 0. Okay, how is this possible? Basically, this, if you ignore the rate term, the rate color V0 term, the expression that you see is the junction capacitance expression we derived earlier, which is here. Okay, all right. Now, if I include the V0 in the numerator and the V0 in the denominator, right, I can then group V0 over V0 minus V square root separately, and the remaining terms that I have left would actually represents the junction capacitance at 0 bias. You can easily see that if you try to manipulate the algebra slightly. Okay, so this is the alternative way of expressing CJ in terms of CJ naught. All right, but it doesn't change the original expression. Okay, right. So this is the CJ naught, right? As you can see, right? When VA is 0, or when the external voltage V is 0, you only have this term V0 here. Okay. All right. So at this point, right, just to highlight that the derivation for the junction capacitance assumes abrupt junction. Why? Because of the expression that we use for W. Okay, we have used the remember this expression for W only applies to an abrupt p-n junction, and this is used in obtaining the expression for the space charge stored Qj. Okay, so strictly speaking, the expression that you obtain here for Cj only applies for an abrupt p-n junction. Okay, now as what I mentioned earlier, in the real p-n junction, we do not get an abrupt junction whereby the doping concentration changes step-like from one region to another region. That is not practical. So in a real p-n junction, the doping profile actually changes gradually. Typically can be approximated by a linear line, right? In other words, the doping concentration changes linearly from one region to another. Okay, so what this slide is trying to compare is the result we obtain for an abrupt junction, which doesn't really exist in practice, to a real junction or the linear junction or linearly graded junction, which is more indicative of a real p-n junction. The difference is not significant. Right, so the red line corresponds to the linear junction, the black line for the abrupt junction. Right. Basically, a similar expression applies in the case of a linear junction, except that the exponent here becomes 1/3 instead of half. Okay, if you are more adventurous, you can redo the whole derivation for a linearly graded junction, all right, to see if you can come to this result. You have to start right from the beginning, right, when you solve Poisson equation. Right, because at a point in time, you need to decide the functional form for NA and ND. Right, in the earlier derivation, I've taken them to be constant. But you can approximate them as linear function of distance in a real p-n junction. And from there, right, you should try to see if you can obtain M to be 1/3 for a linearly graded junction. This is optional, right? So you can try this if you want to, okay? Okay, so let's go through some work example, right, to get a feel of the order of magnitude of the junction capacitance. In other words, how large or how small it is. Right, so let's consider abrupt p-n junction, whereby the p-side doping is 10 to the power 17 per cm cube, and the n-side doping is 8 times 10 to the power 15 per cm cube. Essentially, this is actually P plus N junction, right? Where the P side is doped more heavily compared to the N. Okay, and the area of the junction is 2 times 10 to the power minus 5 cm squared. The size of the p-n junction, basically. calculate the junction capacitance at 0 bias, at reverse bias of 6 volts, and forward bias of 0.7 volts. Okay, in order to do that, you need to first of all determine the built-in potential, because you need to use this in the expression for CJ or in the expression for W. Okay, so we need to calculate the built-in potential. And after that, then you can calculate the junction capacitance. Okay, so let's do the exercise. So V0 is determined as 0.77 volt for silicon PN junction. So at 0 bias, the external voltage is 0, and the CJ at 0 bias can be determined, right? So typically, you will get a number on the order of picofarad. So just keep that in mind, okay? Typically, right? So if you get something that is way off, then you should double check your calculation. Now, what happened when the reverse bias is increased to 6 volts? So recalculate, just increase the value of V from 0 to 6, yeah? Right, and recalculate the thing, you should get this result, right? Which expectedly is smaller than the value of CJ at 0 volt. Right, the reason is very simple, because under reverse bias, the depletion width gets wider. So for a given change in the voltage, the change in the space charge at the edges of the depletion region will be smaller. Okay, now on the other hand, under a forward bias, right, of 0.7 volts, right, the remember forward bias, the V is positive, right? So the CJ becomes 1.85 picofarad. It increases compared to 0 bias and reverse bias. All right, because in forward bias, the depletion width becomes narrow, and for a given change in the voltage, the change in the space charge at the edges of the space charge region will be higher. Okay, all right, so take note of the different trend by which CJ changes depending on forward or reverse bias. Okay, so that completes the discussion on the junction capacitance. Okay, so the next type of capacitance would be the charge storage capacitance, right? So what's the origin of the charge storage capacitance? Now, charge storage capacitance is applicable under forward bias condition. Okay, it's especially important under forward bias condition. It is negligible under reverse bias condition, and the reason will soon be clear. Now, from the earlier discussion, you know that a forward bias will create a situation where majority carriers are injected across the PN junction. All right, the injection happens due to the reduction in the barrier height, and all right, so as a result of the majority carrier injection, when the majority carrier on one side get injected into the opposite side of the junction, let's take for example holes from the P injected into the N. These holes become excess holes in the N region, and they do not disappear immediately. They will start diffusing along the quasi-neutral N region, and as they diffuse, they will recombine. Right. So in other words, under a given forward bias, the PN junction stores excess minority carriers in the quasi-neutral region. Right, excess holes are stored in the quasi-neutral N region. Excess electrons are stored in the quasi-neutral P region. All right, so this excess charge storage is represented in this diagram here. Remember, if you consider one side of the junction, the N side, so holes are injecting from the P into the N, and the excess holes will decay exponentially with distance. We have solved this. The mathematical equation for this line is known. All right, it can be obtained by solving the continuity equation, if you remember. Okay, all right. Now, that means at any particular instant in time, so long as the PN junction is under forward bias, I will have some excess holes stored in the quasi-neutral N region, as well as excess electrons, all right, in the quasi-neutral P region. Okay, now if you now imagine, I increase the forward bias slightly. In other words, I make the PN junction more forward biased. Okay, that will result in more carrier injection. So the amount of holes stored in the quasi-neutral N region will increase. So this increase is represented by the second black line here. Okay, all right. So when the forward bias is increased. All right, so the same applies to the excess electron stored in the quasi-neutral P region. All right, so very clearly, the excess minority carrier charges stored in the PN junction can be changed by changing the forward bias. All right, it increases when the forward bias is increased, it reduces when the forward bias is reduced. So there is a capacitive effect related to this excess minority carrier charge. And this capacitive effect is called storage capacitance. Okay, all right, storage capacitance. So notice that the storage capacitance is not related to the space charge stored, but it is related to the excess minority carrier charge stored in the two quasi-neutral region under forward bias condition. Okay. Now we can also derive, sorry, the order of them appearing is a bit messed up. I'll fix that next time. So essentially, due to the charge storage capacitance, it takes time, all right, for the excess charge stored to change when the forward bias is changed. Okay, all right, so that introduces a delay in the response of the PN junction to an externally changing electrical signal. All right, now we can derive a expression for the charge storage capacitance by considering the total excess minority carrier charge stored on the N side as well as the P side. So let's look at the N side. As you know, excess holes are stored on the N side. Now the total excess hole stored total can be obtained by integrating the excess hole concentration function from 0 to infinity, assuming that the quasi-neutral N region is infinitely long. Right, so we can integrate delta Pn, which represents the excess hole concentration stored inside the quasi-neutral N region from 0 to infinity, and multiply the integral by the charge Q. So that will give me the charge in Coulomb. Right, this integral will just give me the total number of holes per unit area. Right, so if you multiply by Q the charge, right, of each hole, you get a total charge stored. And if you multiply by the area, you get the exact amount of charge stored in the quasi-neutral region. Right, multiplied by Q alone get you the excess hole charge stored per unit area. Right, so you need to multiply by the area A to get the total excess hole stored in the quasi-neutral N region. Now you recall the delta Pn x prime can be expressed like this. This is a result of the solving of the continuity equation, if you remember. Then the delta Pn can be related to the voltage applied across the PN junction by this term here, by this factor here. So you can put this expression inside this integral, and noting that the only term that is x dependent is this exponential term here. The rest are constant term, which you can pull it out of the integral sign. Okay, then it boils down to integrating just exponential of minus x prime over LP. Right, now integrating this gives you, this is an exponential function, so integrating it gives you an exponential function multiplied by minus LP. Okay, all right, and then you evaluate the integral at 0 and infinity. Now after you evaluate it, this integral will evaluate to a value of 1. Right, you can check that quite easily on your own, and therefore the result that you obtain, right, will be shown here, where the LP term is a factor that you need to introduce when you integrate this exponential function. Okay, right. So this is the final result representing the total excess holes stored at the quasi-neutral N side. Now we can repeat the same exercise for the excess electron charge stored on the quasi-neutral P side. Okay, all right. Now there's a negative sign here because an electron carries a negative charge. Okay, and if you go through the similar steps, right, this will be the final result, right, for the total electron charge stored, right, on the quasi-neutral p side. All right, so how do I get an expression for CS, the charge storage capacitance? I need to get the total excess minority carrier charge stored, which is essentially the summation of QP and QN. Now, for QN, it is a negative term because of the negative charge associated with the electron. When we sum out QN and QP, we take the magnitude of QN. Okay. Okay, these two equations were actually earlier repeated here, just for convenience during the discussion of the derivation. Okay, all right. So they have been repeated earlier. So the total excess charge stored can be obtained by summing QP and QN together, and we take the magnitude of QN. All right, now, if we consider the case of a P plus N junction, for example, all right, remember when the P side is doped much higher compared to the N side, under a given forward bias, hole injection will dominate, meaning that the amount of hole injected from the heavily doped P side to the N side is much greater than the amount of electron injected from the N side to the P side. So it is possible to make an assumption here by neglecting Qn, and we keep only the QP term, which is the more dominant term. Okay, all right. Notice at the same time, due to the dominant hole injection, the hole diffusion current at the edge of the depletion region is also much greater than the electron diffusion current at the edge of the quasi-neutral P region. Okay, right? So therefore, we can obtain an expression for CS for this example of a P plus N. So from here onwards, the discussion applies to a P plus N. So in a P plus N diode, the storage capacitance can be defined as dQs over dV. Now Qs is predominantly QP. So this can be approximated by dQp over dV, neglecting the Qn term. All right, so differentiating QP with respect to the voltage V. Now QP earlier was shown to be given by this expression. Where's the V term? The V term is actually embedded in delta Pn, right? Let's see, yeah. So delta Pn at x prime equal to 0, remember, is given by this. That's where the V term is. And it's optional to drop or to keep the 1 because under forward bias, the forward bias voltage V will make this exponential term much greater than compared to 1, right? So you can either keep or drop this. It doesn't really make a difference. If you keep this, after differentiation, the 1 will go away, all right, as well. So by differentiating this term with respect to V, we can then get an expression for the charge storage capacitance. All right, now if you recognize some of the terms can be grouped together in the end, all right, you can express CS as Q over KT times QP. Okay, all right. Now, at this point, take note that this expression only applies to a P plus N. Now, what if you do not have a one-sided PN junction such as a P plus N? If you have a PN junction that has comparable P and N side doping, then it is necessary to consider the Qn and the QP term both together. All right, okay. So in that case, you will have an additional term here for the charge storage capacitance. So there will be one more term plus Q over KT Qn. Right? So you can easily rework this and see for yourself. Okay, now it is possible to express CS in an alternative form based on the same P plus N junction example. Moving on. Now, as you know, for a P plus N junction, the whole current dominates, whole injection current dominates. In other words, the total diode current, which is a summation of the diffusion, the respective minority carrier diffusion current density at the edges of the space charge region, right, can be simplified as follows, where we only consider the diffusion current due to the holes, okay, due to the predominant hole injection over the electron injection. okay, in the P plus N diode. Right, and we can re-express this by noting that LP is actually defined as a square root of dp tau p. This was done much earlier, right? So if we make use of this definition for LP, then it is possible to express the ratio of dp over LP to be LP over tau p. You can see for yourself, right? If I square both sides, I will get LP squared equals to dp tau p. And from there, you can see that dp over LP can be expressed as LP over tau p. Okay, now if you look at the numerator term, right, it is none other the QP, all right, representing the total amount of holes stored in the quasi-neutral N side. So the total current I flowing through the diode in this example of a P plus N can be expressed as QP over tau P. All right, and based on this, therefore, QP can be expressed as I multiplied by tau P, and therefore the CS can also be alternatively expressed as Q over KT times I tau P. This I tau P product term is actually QP. Okay, so this is just an alternative expression for the storage capacitance for a P plus N junction. Now, again, for a normal PN junction where you have comparable doping concentration on the P and N side, you will end up with a additional term here. In that case, this has to be IP and not the total current I. Right? This will be IP itself. Okay, so please take note. You can rework this derivation to see for yourself what the CS expression would be for a normal PN junction with comparable doping on the P and N side. Okay. Now, since CS is proportional to QP for P plus N, and it is proportional to I, the total current flowing across the PN junction under forward bias, and I is typically large, okay, CS can be very large under forward bias, right? In fact, CS depends exponentially on the forward bias voltage, meaning that there will be a large change in the amount of charge stored when you change the forward bias by a small amount. This exponential dependence comes from the exponential dependence between the carrier between the carrier injection with respect to the applied forward bias voltage. Now, because CS is large, it will cause some problem in terms of the switching speed of the PN junction, especially in high frequency application. I will give you one example to more clearly illustrate this. Okay, so the total capacitance across the PN junction therefore has two parts, right? One is the junction capacitance, the other one is the storage capacitance. Okay. So under forward bias, CS is dominant, so CJ becomes negligible compared to CS most of the time, and the total capacitance is dominated by the storage capacitance. Under reverse bias, CS becomes very small, negligible compared to junction capacitance, and therefore the total capacitance of a diode under reverse bias is given by the junction capacitance. Okay. Now, as mentioned many times, the presence of these capacitances will limit the operation of any circuit using PN junction diode, because the PN junction diode themselves need time to respond to the external changing electrical signal due to the presence of these capacitance. Okay, let's do a simple work example to get a feel of the order of magnitude of storage capacitance. All right, let's use back the same PN junction as we use for the junction capacitance. Right, so the doping concentration are the same, unchanged. The area of the diode is also the same. Right, so the lifetime of the holes is given in the quasi-neutral N region is given by 0.1 microsecond. The diffusion constant, or the diffusivity, or the diffusion coefficient is 16 cm squared per second. Calculate the storage capacitance for two different cases, 0.6 forward bars and 0.6 volt forward bars. Right, so you can recall the expression for CS. Right now, so there are some terms that you need to calculate before calculating CS. One of them is PN0, the whole concentration at thermal equilibrium in the N region. which is Ni square over Nd, assuming full complete ionization, and Nd is much greater than Ni, so it can be used to approximate the electron concentration in the N region, right? So this is from the law of mass action, if you may recall. All right, so this is Pn naught, and Lp can be calculated from the definition dp times tau p square root. Since both are given, you can calculate Lp. Okay, so with that, you can calculate Cs at different forward biases. Right, so Cs at 0.6 volt forward bias is 20.4 picofarad. This is already much larger than the junction capacitance. Right, you can refer back to the junction capacitance that we calculated earlier. Right, and when you increase the forward bias by just 50 millivolts, right, notice how Cs has changed. It changed like 6 times to 7 times, right? 6 to 7 times because of the exponential dependence of Cs on the forward bias voltage, which can be traced back to the exponential dependence on the carrier injection across the junction as a function of the applied forward bias voltage. Okay, all right. Okay, this is already very big. So if you try to calculate Cs at 0.7 volts, you will get even bigger. And in fact, earlier on, we calculated Cj at a forward bias of 0.7 volt. It is only 1.85 picofarad. Right, so this confirms that under forward bias, Cs dominates the total capacitance. Okay, now at this point, I just want to give you one example to illustrate the importance of the storage capacitance, how it can slow down the turning off of the PN junction. Okay, so this example will take about five minutes. So with that, I think we can finish almost on time for today. Okay, to illustrate that, we can use a circuit like this, which is very simple. You have a PN junction here, right? At first, the PN junction is forward bias, so the switch, this is a toggle switch. So at first, the switch is connecting to this part of the circuit, forward biasing the PN junction like this. Right? Just take note of the polarity of the voltage applied here, right? So that creates a forward bias. So as you know, under forward bias, a large current flows, right? And at steady state, if you examine the excess minority carrier concentration profile along the PN junction, it will look like this. So the excess holes will decay exponentially with distance into the quasi-neutral N region, and the excess electrons similarly decay exponentially with distance into the quasi-neutral P region. Okay. Now, this drawing where the concentration of excess electrons and holes at the edges of the space charge region, right, are taken to be equal is arbitrary, right? Because in this example, we assume the P and N region to be equally doped. So these 2 points need not be of the same value, okay, right? Now imagine what happens when I suddenly toggle the switch from this position to this position at a time t equals to 0, which I define as 0 seconds, okay? Now, if you examine how the external voltage is applied, okay, in this case, the polarity of the applied voltage is such that it will try to reverse bias the PN junction. In other words, the PN junction should turn off when I toggle the switch from this position to this position, because in this position here, the applied external voltage is reverse bias. Okay, right? Now, when the PN junction turns off, the current should be very small. So the question here is that, does the current immediately drop from a large value to a very small value the moment I toggle the switch from left to right? The answer is no, and because of the presence of storage capacitance. Okay, so why is that the case? Now, because of the presence of excess minority carrier charge stored in the quasi-neutral region, even if you toggle the switch trying to reverse bias the PN junction at time t equals 0, the excess minority carrier charge stored cannot disappear immediately. Okay, so at the very time you toggle the switch, pretty much the same excess minority carrier charge is stored on both sides of the junction. Okay, so in other words, even if you toggle the switch from left to right, the diode remain forward bias. Okay, all right. Sorry, you can think of the diode to remain forward bias, but the direction of the current can change. And the current flowing through the diode can be also quite large, because the current can be supported by the extraction of the excess minority carrier charge stored. Remember, under reverse bias, there will be an extraction of carriers across the junction. But since there are excess minority carrier charge stored, right, they can be extracted across the junction, supporting the large current that can flow for a short period of time. So as the extraction continues, of course, the excess minority carrier charge stored will decrease with time. And essentially, it will approach the steady state condition, right, shown by the dashed line here. If you look at the dashed line, it corresponds to the earlier discussion that we had on how the excess, how the minority carrier charge concentration would vary across the junction under reverse bias, right? So that is the point in time when the diode current will approach the reverse saturation current of the reverse bias PN junction. So as you can see, due to the presence of the storage capacitance, which essentially relates to the storage of excess minority carrier charge stored under forward bias, the diode does not turn off immediately. When you try to toggle the switch from left to right, the diode does not turn off immediately. There would be a certain finite time where a large current can continuously flow, right, across the diode, although in the opposite direction, before it decays to a very small value, which is the reverse saturation current value at steady state condition. Okay, so through this simple example, you can easily see how storage capacitance affects the turning off transient of the PN junction. Right, it is not possible to immediately turn off a PN junction due to the storage capacitance. Now, the storage capacitance also affects the turning on speed of the diode. You can imagine during turn on, right, the excess minority carrier charge stored does not build up immediately to the final value at one go. It takes time to charge up the storage capacitance. In other words, it takes time for the majority carrier to be injected across the junction to form the steady state profile shown by the black line. Okay, so because of this finite time needed, the diode current does not increase immediately to the forward bias current the moment you toggle the switch back to the left position. So there will be a time whereby there will be a delay time whereby the current actually increases towards the final value of the forward bias current. Okay, so through this simple example, you can appreciate why the storage capacitance is important in determining the turning off and turning off speed of the PN junction. Okay, right. So with that, that concludes this part of the discussion on junction capacitances. So to summarize, there are two types of capacitances: junction and storage capacitance, right? And storage capacitance will dominate under forward bias, whereas junction capacitance dominates under reverse bias. Okay, it is the storage capacitance that controls the transient response of the PN junction, and therefore this becomes an important consideration if you try to use a PN junction diode in a circuit that is meant to operate at high frequency. All right. Okay, so with that, we finished today's class, and okay, yeah. All right, so I hope you're okay. Are you still around?
Prof. Prof, can you hear me?
Okay. So your question? Yeah, I can hear you.
Hello. Yeah. Okay. Yeah, for the junction capacitance, right, does it affect the transient time taken for the PN junction? Like, say if you apply a reverse bias voltage in the start, right, which means the junction capacitance dominates at that point
Yes,
in time. But then
yes.
if you switch off the current supply, would there be a transient time like similar to how there is one for the storage capacitance?
Oh no. Okay. In the example that we saw, turning off transient, the current is predominantly controlled. The transient current is predominantly controlled by the storage capacitance because this capacitance is much larger compared to the junction capacitance. Of course, in principle, yes, there will be some redistribution of the charges to change the width of the space charge region required to correspond to the steady state value. Yes, but this actually is not significant compared to the transient related to the storage capacitance.
What if the PN junction is in reverse bias?
Yes, so let's say you reverse bias the PN junction and you're trying to switch it to forward bias. So during the time when the reverse bias is trying to go towards forward bias, yes, there would be a redistribution of the space charge needed to correspond to the change in the applied voltage. Yes, during this time, the response is controlled by the junction capacitance. But the moment forward bias is reached, where carrier injection happens across the junction, the further increase in the current will be controlled by predominantly the storage capacitance because this is much larger compared to the junction capacitance.
Okay, yeah, I get that. Thanks.
Okay, right. So I will unshare the screen. If you have any question, feel free to ask.
Hi, Professor.
Yeah.
Sorry, I just want to check because I was absent for the lab two due to I was having a fever. So, but I've emailed Prof. But haven't received any information about the makeup.
Oh, so you have a valid MC.
Yes.
Yeah. So eventually a makeup session will be arranged. It's just that we need to find a suitable time for you
Oh.
to come here because at the same time the lab is also used for the full-time undergraduate student.
Yeah.
So he's probably trying to arrange a suitable time to do the makeup.
Okay, I'm just worried because I didn't receive reply from him. Yeah. Thank you.
Has it been some time since you sent the email?
Yeah, like almost a month.
Almost a month. Okay, then I think you can drop him a reminder email.
Okay. Okay.
Okay.
Thank
Yeah.
you.
Okay. So
Hello, sorry,
yeah.
Professor.
Yeah.
Can I ask, right, for the diode turn-off transient thing at the last slide,
Mm.
why is there the TS where the current remains constant?
Okay. Okay. Let me get back to the slide. Are you referring to this current here?
Yes.
Okay, this is approximately constant. It's not strictly constant. It can be thought to be approximately constant because during this point in time, the carrier extraction is controlled by the profile of the excess minority carrier, and in particular the slope here, right, which determine the back diffusion of the excess minority carriers towards the junction. And this slope is approximately the same for different instances of time, as shown here. So the back diffusion of the minority carriers is approximately constant. Strictly, it's not constant, right? It's just assumed to be constant, and it can be argued to be approximately constant by virtue of the very similar slope in the minority carrier profiles here. Before the concentration reaches equilibrium, and once it drops below that, then the current will start to decay significantly towards the reverse saturation current value, which is controlled by the slope of the minority carrier profile here.
Oh, okay. Thank you.
Right. Okay, thanks. Any other questions? If not, we can call it a day. You can log off. If you have questions along the way, you can send me an email. Right.
Thank you, Prof.
Okay. See you guys.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.
Thank you, Professor.
Thank you, Professor.
Thank you.
Okay. See you. Bye bye. Okay. So I will log off now. So see you guys. If you need to contact me, just send me an email. All right. Okay. Bye.